Hey guys, so this will be the third lesson for today. Again, this should also be review of stuff covered by Mr. Morrison last, well, whenever you took Physics 11. For some of you, it'll be earlier this year. For some of you, it'll be last year. So the Atwood machine is basically it's a pulley system. As far as we are concerned in physics, there's a few things that we want to always make note of. First of all, there is no friction in the pulley. We all know, practically speaking, pulleys will hit friction. Um, we're going to operate under the assumption that there is none because it gets really hard if we have to account for friction. We also have to acknowledge that in the real world, they're almost frictionless. Like there's the friction amount of friction is very, very little, just due to the fact that they're greased up and all that kind of stuff. So no friction. We're going to assume this is on or near Earth. That allows us to make some assumptions. Another assumption we have to make, the rope / chain, whatever it is, has no mass. If it does, this gets really difficult. This becomes a differential equation, and you need several layers of calculus to attempt it if the rope has mass. So as far as we're at, we're going to assume that the rope is massless, there's no friction in the pulley, and this thing is on or near Earth. And these assumptions lead us to one final assumption, that the heavier mass, and this makes sense based on everything we've assumed up to this point, the heavier mass dictates motion. Which I'm hoping is obvious. If I have M1 and M2, you know what, no, we'll leave it like that. Let's go here. If I have equal masses placed on both sides of the Atwood machine and one mass is lifted higher, when released, how does the system move? Keeping in mind the assumptions that we've made before. Okay? If the rope has mass, it should be obvious what happens here. But if we ignore the mass of the rope, and I've got equal masses, if I set the system up like that, what should happen? Well, if we are ignoring the mass of the rope, let's add some forces here. If we ignore the mass of the rope, comma, let's see what happens. I'm going to have Fg acting downwards there, and I'm going to have Fg acting downwards there. If these masses are equal, these two Fg's are equal to each other. So I've got equal forces pulling down here. When I let this thing go, ignoring the mass of the rope, what will happen? Well, you should all at this point be saying nothing. Nothing will happen because my forces are equal and opposite, so nothing should happen. The system will remain at rest. As the forces are balanced. Okay? Ignoring the mass of the rope. Flip the page. We are not going to do that example. We're just going to go straight. I want you to flip straight to page 107. I'm not doing this example here, but I want to use this blank space. So scribble out example 4. We're going to do one example combining the previous lesson and this lesson. Again, pulleys, the purpose of the pulley is to change the direction of a system. This should not be, this lesson's not overly advanced. Let's take a look at the example that I'm about to draw here. So first, what I want you to do is I want you to put a table over here. And we're going to put a pulley on the table. We're also going to put a pulley up here. So there's the framework for our problem. And now we're going to draw some blocks. We're going to put a block over here. We're going to put a block back here. We're going to put a block here. We're also going to put a block here. And we're going to put a big block over here. And now we're going to connect them with some rope. There. That is the system. This, starting from left to right, this is going to be a 10 kilogram block. This is going to be a 3 kilogram block. This is going to be a 2 kilogram block. This is going to be a 5 kilogram block. And this is going to be a 2 kilogram block. And we're going to say that there's a coefficient of friction here of 0.1. A moderate amount of friction. And we want to find the acceleration of the system. Okay, so we're just using the tools we used in the last lesson and looking at some of these pulleys here to tackle a question like this. So starting on the left, working our way kind of down to the right, following the rope, we're going to start to free body diagram this. There's a force of gravity downwards here, and we're just going to start putting values in here right away. Fg is mg, g is 9.8, mass is 10, so this is going to be 98 newtons. And this guy is going to have a force of tension 1, because I'm going to call that block 1. I'm going to call this block 2, this 3 kilogram block here. There's a force of tension upwards here. It's the same as this tension, because that's the same string. This guy's going to have an Fg downwards. Fg on this guy is 29.4, 3 times 9.8. And he's going to have a an Ft2 downwards. This guy's going to have an Ft2 upwards. And he's going to have an Ft3 downwards. And he's going to have an Fg downwards. 2 times 9.8 is 19.6 newtons. This tension is the same as that tension, so it's going to be Ft3. He has a normal force acting straight up because he's sitting on a surface. He has gravity acting straight downwards. The value for gravity there is 49 newtons. And the normal force here is also going to be 49 newtons because this tabletop is level. Nothing weird happening there. This guy here, oh, and there's a tension, force of tension 4 backwards there. Force of tension 4 going to the left there. There's Fg downwards of 19.6 newtons. There's an Fn upwards of 19.6 newtons. Oh, and on both of these, I forgot already to include tension. Sorry, friction. This guy's going to have a force of friction. Block 2, that's block 3. Block 4. So force of tension on block 4 is going to equal 0.1 times Fn, so that's going to be 4.9 newtons. And this guy's going to have force of friction for block 5, and that's going to be 0.1 times 19.6, so that's going to be 1.96 newtons. So I've got all my free body diagrams, with all my forces on everything, and now we're just going to sum them up. I'll do this in a little bit if that would help. There you go. So I'm starting with this F net equals MA. Block 1. Oh, right. And I also haven't said which way is positive. If this system is going to move, there's a couple options here. This guy could drop and pull this thing up and over, and these guys would slide this way. It would stop when it gets, this block gets hung up in that pulley. Or these two are going to drop this way, pulling these ones in and this one up and over. Now we should be able to see that this is obvious. This is 5 kilograms, this is 10 kilograms. So this is going to pull down here, pulling these guys up and over if the system moves at all. We don't know what's going to happen here with the frictions from these blocks on the side. So I'm going to say that positive is going to follow that blue line there. Okay? So here we go. The blue line's going up, over, and down, so that 98 is positive. So it's going to be, I'm just going to put the values in it this time. 98 minus FT1 equals 10A. Block 2. It's going to be FT1 is positive based on the direction here, minus FT2 minus 29.4 equals 3A. Block 3 is going to be up is positive, so it's going to be, I'm going to have a positive FT2 minus FT3 minus 19.6 equals 2A. Block 4, I've got FT3 minus FT4 minus 4.9. Fn and Fg don't act in the direction of motion, so I don't have to include them in this F net equals ma equation. Equals 5A. My last block there, number 5. I'm going to have FT4 minus 19.6. Nope, 1.96. Equals 2A. If I sum these equations up, we're going to see my FT1s, positive and negative, are going to cancel. My FT2s, positive and negative, are going to cancel. My FT3s, positive and negative, are going to cancel. My FT4s, positive and negative, are going to cancel. So I'm going to get this. 98 minus 29.4 minus 19.6 minus 4.9 minus 1.96 equals 10, 13, 14, 15, 22A. Sum that up, divide it by 22. You're going to get that 42.14 equals 22A. So A equals 1.92 meters per second squared. That's positive. So that tells us that this, if this is positive, this system is accelerating up and over. Not very quickly, but it's still accelerating. So that's it. This lesson's pretty short. The homework I'm going to get you guys to take a look at here is the following. If we were in class, I would do example 6 because it's really quite cool. But we're not, and I don't really have the camera equipment to really show how this goes. But yeah, it's cool. Try it if you're into it. If you've got a pop bottle at home, give it a shot. Same thing with 1. If you've got a pop bottle at home, try that exercise there. So this is going to be part of your optional, we'll call this optional homework. Example 6 and number 1. Try it if you've got a pop bottle at home. See if you see if you figure it out, and then give it a shot. If you do manage to try it, make a note of it in the homework that you submit. But this is the non-optional homework I want you guys to do. Oh yeah. Two, 3, 8, and 9. No, let's do 4, 2. 2, 3, 4, 8, and 9 is your homework for this lesson. As always, if you have questions, let me know. This, again, hopefully is all review. If you did summer school physics, this might not be, and then you need to come get help. But if you had class with Morrison, this should be review. So we'll move on to the inclined plane stuff starting on Monday. Good luck this weekend. Hopefully this makes some sense. If it doesn't, feel free to email me. Have a good one.